Okay, so let's get started here. Before we start, just have some general questions. Do you have any suggestions here regarding what I should cover later in different sessions? Based on my experience, let me start with what I think of first. Based on my experience, I feels like I feel like it's a little bit too much material for each week if we only cover every other week. If I restart over this course, I would probably would rather to have a session around 30 to 45 minutes every week. That's my feeling. That way we can be a little bit more focused um, on the material for the specific week. The dilemma that I'm currently have is if you guys have not read anything before the session, it's very difficult for me to teach. But the thing is, it would be very difficult for you guys to read anything before Thursday because you only rushed through the last homework and then you kind of feeling that you want to have a rest. Plus, you guys are working during the daytime, so I kind of feeling that it's very difficult for you guys to have read anything before Thursday. So that's kind of what my feeling is. So you guys have any thoughts on this?
You are correct.
Yeah, go ahead, Pastor.
No, that is exactly we have the problem because the timing and all other thing, and particularly this semester, both the papers we have a lot more to study, and making time or getting time is the biggest challenge.
I see. So for previous semesters, in terms of courses, um, would you say that is it fair to say that this course has more workload comparing to the rest of the courses previously that you guys have taken?
That's correct, and that is on both the papers. That is this modeling as well as probability statistics.
Both of these two courses, I see. Yeah, yeah. I think one thing that I feel it's difficult for this course is it has too many material, meaning that a lot of concepts are in a course, and then we can only touch upon the major ones for each week. So I'm trying to be more uh, I'm trying to provide more guidance on what we are covering each week, but I still feel it's kind of difficult. Yeah, probably in the future, when I start teaching this course again, I'll probably start like 30 minutes to 45 minutes each week instead of every other week. Meaning that for an hour, it's very difficult to cover a lot of material. So, you guys have any other thoughts if you want to share? No? If not, so let me get started here.
If you're monitoring the chat, some have mentioned having an extra meeting to cover the material.
Extra, James is that James talking? Vincent, right?
No, this is Vincent. Yes.
Yeah, Vincent, go ahead. What was your suggestion?
Possibly have another meeting some other day of the week.
So are you suggesting twice a week or once a week?
Once a week for this class, I think.
Yeah, I think let's do that, right? Maybe from next week, let's do. I don't know if it's in terms of schedule, if that's a problem for you guys.
I guess it can't be at the exact same time just because of the other class.
The other class is on the odd weeks, right?
Right, at the same time.
Okay, so maybe as Shrad suggested, maybe odd week on Thursday and the even week on Wednesday. I'll talk to Paul and see possibilities. Okay.
Okay.
Okay. And also office hour is actually fine. If you have any questions, I can answer, and we can even schedule some Skype sessions if you want to. And in terms of extra credit, I really don't, don't worry too much about the grade and everything. As long as you work hard on the course, I don't see any problem for you guys to get a really decent grade. Okay. So what I did was I wanted to prepare some linear regression example and some simulation example, but I wasn't able to get it ready yet. But I really got something, some linear programming example that I would like to share with you guys. So let's do this. First of all, I'll start explaining what's in the week 6 and week 7, and then because next week will be week 8, hopefully we can talk about we can talk about week 8 next week as well. But for week 6 and week 7, I believe, although you have already finished homework 6, but I feel like we should cover more on the content there, especially we didn't cover the week before. So let me get week 6. So I have muted all of you guys. So if you have questions, you can either type or raise your hand so that I can answer questions. So let's go to the slides for week 6, which was last week. Of course, if you have any questions regarding the homework, etc., you can ask as well. So let's go here. Okay. So which screen are you looking at? This one? Is this a screen that you can see, or you can see both? I have 2 screens. Oh, you can see both. Okay, that's fine. Then I should just leave this here. Okay, so in week 6, we will really started the math modeling piece, which is optimization. And then let's look at an overview of the optimization modeling. Oops. Okay, in chapter 3, remember that when we did the linear regression, we said that some possible criteria that we can use for fitting a selected model to a collected of data. Right? One possibility was saying that we can minimize the sum of the absolute deviations, and then we can also minimize the largest of the absolute deviation. And then the other one that in linear regression, we specifically said we're going to minimize the sum of the squared deviation, which is a least squares criteria. And it happened to be that this last criteria itself is a minimization problem, which happened to be a quadratic programming problem. meaning it's not linear, and the objective function is quadratic, which is x squared, essentially meaning. Okay, so let's look at the definition of a linear model. So a linear model is saying that we have objective function and minimize a specific function with some set of constraints. As the name itself stands, it's all linear, meaning that the objective function is linear and constraints are linear as well. So this is even a more general form of linear optimization. So as you can see, a couple of things. One thing is it has an objective function, and also it has decision variables. X in this case would be the decision variables, and it has a set of constraints. And also there is something specific says on the right-hand side. Those are all the basic components or concepts for linear programming. So optimization problems have multiple types. It could be classified as unconstrained or constrained. As constrained, as you see here, it's constrained. If we don't have all these constraints, then it's unconstrained optimization problem. And then what is a linear program? It is there is a unique objective function, and decision variable has power of 1, i.e. it's in other words, it's linear. And it's no product of decision variables in the objective function or constraints, meaning it doesn't have anything like x1 times x2 or x1 squared or x1 times x3, so on and so forth in the decision variables or in the constraints. And then the coefficients of the decision variables in the objective function and its constraints are constant. Also, the decision variables are permitted to assume fractional as well as integer values. So it's fractional, fractional. That's called a linear program. And later we would learn a little bit on the integer program, meaning that the decision variable will only be allowed to be integer values. That's a totally a different area that we need to study later. So as I said here, there are some other types of programs, multi-objective or Go programs or nonlinear program, dynamic program, stochastic program, or integer program. Many times it's mixed integer program, meaning that it can be integer, can be a fractional number as well. So that's why it's called mixed integer program, which is also called MIP in many cases. So here are some very specific example, and I'm going to go through a very detailed example in R later. So I'm not planning to go through these examples, but I assume you guys have already read this. So, and here is a very interesting example in the book. Says that we can approximate by a piecewise linear function, meaning that if we approximate all the pieces into a different linear function, then we can kind of model this problem as a piece linear function and solve it using linear programming approach. And very important concept here is a feasible region, meaning that all the constraints set up a region. For example, you know that 5x1 plus 4x2 less than 120 is actually this line, right? And then this one is the other line, which one is this line. So that, and also we have x1 larger than 0, x2 larger than 0, so that everything has to be on this side and this side. This would be a feasible region. And then your objective function is this dotted line. And then dotted line, if we say, okay, we want to maximize the value, as we all can see, it would happen here. Because whenever, if you continue to move here, it would be less for the objective function. If you move to the other side, it's outside of the feasible region, meaning that it's not a solution for the optimization problem. So, and the reality is for a convex problem, convex meaning not concave. If you have a function like a feasible region looks like this way, meaning it's a quadratic function like that, and then everything down here is a feasible region. No, it's no longer convex. Convex essentially meaning if mathematically speaking, it says that if you pick any 2 points in the region, and a linear combination of those 2 points is still in the region. So it looks like very yeah. Actually, I can later I can show an example for you as what is non-convex. But in general, the linear programming has a very interesting phenomenon, that is, as long as it's convex, then the maximum or minimum will happen. I was trying to, but maybe on the right hand. I don't know. Do you see my cursor now, Aaron?
Maybe.
Can you see my cursor?
Nope, I don't see it.
Still
Maybe it's
not?
just me. I don't know. Oh, now I see it.
Oh, probably you can see on the right hand side, not on the left. I mean, on the left screen, not on the right screen, because I was pointing to the right side. Okay, so let me start over. But in general, I was saying that if this is convex, but if it's concave, meaning something like this, and then everything below, then that's concave, meaning it's no longer any points in on the graph. And if you pick 2 points in the graph, the linear combination of those 2 points is no longer in the feasible region. So for a convex problem, linear problem, all the maximum or minimum will be in the on the boundary points, and also most of the time it will be on those 4 vertex. That's a very interesting phenomenon that you should pay attention to, and you would see that very soon. So here says solution, and so essentially here, just as I explained earlier, that's objective function, that's feasible region, and moving along these lines to pick the maximum and minimum. So, and then there's some theorem to prove that the maximum and minimum would happen at the intersection points of the constraints. That's why a solution method for if you algebraically solve the problem, what you need to do is all these steps. It is find all intersection points of the constraints, determine which intersection points, if any, are feasible to obtain the extreme points, and then evaluate the objective function at each extreme point, and then choose that. But apparently, this is almost like enumeration. There is something better, which is the simplex method. It's a Tableau method. And then actually I didn't get a chance to see your homework yet. I hope you guys get a chance to visit that piece, which is it's not that hard. It's more like pivot table and trying to solve the problem that way. But I can go through some examples if you have any questions. That's exactly what I'm saying here. Go through these examples, and then you would know how to use simplex method. And then very important concept here is sensitivity of optimal solutions. 2 possibilities. One is what is the effect of changing the value of the profit for each table, one of the decision variables. And then the other possibility would be a question of changes in the amount of resources available. What is the change of the objective function if extra resource is available? And there's some economic interpretation here that can help you on this regard, which is the marginal value. This is not really that important. I'm not going to go too much detail here, but that's the idea. Some numeric search method. I hope you guys probably already covered some of this in undergraduate school, but that's not really too much focus for this course. That's the gist of chapter 7, and then let me go through chapter 8 rather quickly, and then we can go through the example that I prepared. Oh, yeah, we should go to week 7. So for week 7, it's an extension of linear programming, although people call it as part of graph theory, but graph theory itself started with linear programming. So it's a natural extension of linear programming. So let's look at some examples on graph, and also some examples on the connection of graph to math programming, which can be very interesting. And okay, use graph to model math problems and connections between graphs and math programming. So there's some examples there, right? So for example, if these are some cities, A, B, C, D, E, F, G, or here in this particular example, it's I believe it's bridges, right? And then if now we can try to represent the whole network as a graph problem, and then we have node. Each one capitalized A, B, C, D would be the node, and non-capitalized A, B, C, D, E, F, G are the edges. And very important concept, edges and nodes. This is something that can be very useful later on in some of the paper or some of the even very popular topics on social network analysis. That's basic for how to represent a graph. And then, so here there's an example here on the book. On the book it says graph coloring. Given a generic map, is it possible to color it with 4 colors so that any 2 regions that share a common border of length greater than 0 are assigned different colors? And it turns out to be this is one of the solutions for the US map. If we use all these different shapes to represent the different color that we talked about, then this would be one of the solutions. So we have all these 4, and then the one that is connected to all of them is a different shape or different color. So as just mentioned there, nodes are also called vertex set, meaning all the points on a graph. And then the other thing is called edge set, all the edges that's connecting different nodes or different vertex. And incident and adjacent. Incident is actually meaning that all the edges incident to A, for example, for this example, we say what are the incidents that's related to node A. That would be C, D, A, B, and E in this case. And next concept is adjacent. Adjacent would be the nodes that's connected with each other by a single edge. Degree is defined as a number of edges that's incident to a specific node. In this case, for degree of for this particular node A is as you can see, it's A, B, C, D, E, so it's 5, and then the degree for D would be 3, which is G, E, and F. Graph models, how to fit a piecewise linear function to a data. See, we talked about this earlier. It could be overfitting in this case. If you fit every single point, it's just too much. We probably don't want to do that. And then there's another possible solution, which is a linear function. And then in general, looks like this one is better, in my opinion. If you have studied them previously, as some of the homework said, right? This one probably would be the best solution. It depends. It's relatively more complex than the first solution as well. So you can argue that the first solution might be the best. But in some regard, we definitely think that the second solution is not the best solution for this case. This one is some graph solution based on cost structure. So there's many ways to model problems. For example, if we think about road network, transportation network, right? Every single node could be a single intersection, and then all the edges would be the distance or travel time between those intersections. That way, we could study something like the shortest path between 1 to 5 to 1 to 6, or different possibilities. And that's one example. There are some other examples on network analysis as well. We actually would see more example very soon, I believe. And then this is a softball example in the book. If you haven't read it yet, but I can just want to explain to you what's the idea there. So idea there is, say, a single player, they can be, suppose that in a softball game, there are 11 possible positions. And then A1, Al, right? Maybe Al, yes. Al can assume position 2 and 8. I believe this is Al, yes. Yes, that's why, meaning that he is capable to do 8 and 2. And then Bo can do 1, 5, 7. So B can do 1, 5, and 7. So there is a link in between them. On the left-hand side, that's all the players. On the right-hand side are all the possible positions. And then if we have a link, meaning that they are able to play that position. And then if we say that what's a solution, what's a feasible solution, or what's a optimal solution, given that if we say that the cost or the benefit of different link is different. If Al can play 8 and 2, but he play 8 much better than play 8. He can play 8, but not necessarily he is best on 8. So in that case, if we can assign some cost or some benefit on the link between A and 2, between A and 8, and between all other edges, and then we would be able to find the minimized cost or maximized benefit for the team as a solution. That's a perfect example for a classic graph model, which is called matching. Okay, you guys would be able to read the book. I'm sure it's very interesting. Hope you would appreciate the concepts and these interesting ideas. And very similarly, along the line, that's saying that it's a vertex covering problem, saying that if I only have 2 police stations in the city, and then I want to cover all the relevant nodes in the city, or the relevant neighborhoods, let's say, then how can we assign what's the possibility for us to assign who is covering which neighborhood, or which station is covering which neighborhood. That's another example called vertex covering problem. And then here is, this is one of the focus for this chapter. Actually, I'm sure I have an assignment on this, which is the shortest path algorithm. I'm not sure if you guys got any opportunity to study this. If you studied a little bit on data structure in the computer science program, you would learn this as well. It's a classic example, meaning that how do we find the shortest path in a network from a certain points, or from multiple points. I'm going to show you some example after these slides. Also have maximum flow problem, solving bipartite matching problem using maximum flow problem, which is also happen to be an example in the book, which is an important concept as well. But traveler salesman problem, that's the next one, which is TSP. it's actually a very difficult concept. I don't know I don't think you should spend too much time here, but I hope you can understand the idea. So the idea basically is as a UPS driver, if he starts at location A, assume that his base is A, he needs to visit all the locations B, C, D, E, and then come back to A. But which would be the best route for him? Starting with B, C, D, E, and go back to A, or starting with E, go to C, and go to B, and come back to D, and then go to A again. So that's the traveler's salesman problem, but it's not an easy problem to solve. Just want you to realize it's actually a complex linear programming problem, and then there are so many computer solutions, computer programs to help you to solve the problem. At least I just want you guys to get a sense that it is a linear program, and mathematically it can be represented as a linear program. And there are some more, yeah, I'm not sure if I should go through these details, but I can roughly explain what's happening here. So vertex cover is actually saying that every single node should be covered. If we use an example, let's see. Okay, from I to j, if a single xi is the node I and xj is node j, meaning that xi plus xj larger than or equal to 1, essentially meaning that at least one of them should be covered, right? And then there is a minimization of the problem, but it's better that if we have a graph. Let me see if we have it here. No. That's the idea there for the vertex cover. And the maximum flow is saying that anything coming to a node, coming into a node should eventually go out. So anything goes in from I to j, sum of all of them over I, meaning everything goes to j, would eventually goes back to some other k from j. So that's the idea here. So that's meaning that this constraint is called conservation of flow, meaning everything coming into this node would eventually go out to some other nodes. So it's called conservation of flow, and it's also called flow conservation. So this also happens in real-world example in transportation network, for example, right? Any car that goes to an intersection eventually would goes to the intersection from other routes, from different routes. It eventually will go to some other nodes through different routes. That's the idea here for this flow conservation constraint. That's for chapter 8, and let me show you some example. It happened that I studied this a little bit more. So let me ask you guys, because last week the homework was related to LP. So did you guys get a chance to use LP solve yet or not yet?
Yes.
So you already started using LP solve.
Yeah.
Cool. So, but I still want to go through this here in general. Okay, so I have an example that is to see. Actually, you have it here. So this is an example that I found. Basically, I looked at some examples on the internet, and I found this is it's rather complete example and very interesting here. So that's a link of the example, and I did a little bit of work on there to replicate this. So so it says that a trading company is looking for a way to maximize profit per transportation of their goods. And the company has a train available with 3 wagons, and when stocking the wagons, they can choose between 4 types of cargo, each with its own specifications. How much of each cargo type should be loaded on which wagon in order to maximize profit? It's a long explanation there. Actually, I have that on the Blackboard. I hope you have it on your computer as well in case you want to read that. And then, so the idea essentially is here. If after you look at this table, you would understand, right? For each train wagon, it has different weight, 3 types, and then each type have different weight capacity and a different space capacity. And but for the cargo, it has 4 types of cargo, and for each of them have a certain weight and also volume. When we carry each unit of C1, what's the profit for each unit of C1, cargo 1? So as you can see here, we would have 3 sets of weight capacity constraints, meaning that we have to satisfy this, and satisfy this. Also, volume capacity constraints, which would be the space availability, and limited availability per cargo type, because we only have 18 tons of C1 in that case. So in terms of modeling, we could always use X or C. In this case, they used C in the example. I'm saying that because each C1 would give us 3,000 units of, each ton of C1 would give us 2,000 of profit. And then each C2 would be 2,100, 2,500, so on and so forth. And then this would be all the profit available, for what? Okay. Because we have 3 train wagons, and this example is not. I mean, in terms of the solution that they give, is not the best, but they give the idea. So idea is for each cargo type, it can go to one of those train wagons. So essentially meaning that it can be C1 on on the wagon 1, or C1 on W2, C1 on W3. So that's why we have 12 decision variables. And then among those constraints, the first one is the set of the availability of the cargo. And then second one is the first one is actually capacity constraints, 10, 8, 12. So that's it's a weight constraints, weight capacity constraints. The second set, those set are the space capacity constraints. And then the third one is the availability of the cargo that we can carry. And then using the LP model, you probably have already done this, but I can show you here what happens if we solve that LP model. When it returns 0, this implies that it's an optimal solution found. And then we can use some of these functions to get the value of the objective function, and also we can get the variables. Meaning that the first one we only have 0 units, second one we can put on 5, so on and so forth. And then meanwhile we can get the constraints of the coefficients of the can get constraints. Actually, I couldn't remember what's this for, but in general, that's the idea. So let's go through this here. This is RStudio. I'm not sure if you guys are using. If you haven't, try to use RStudio when you get a chance. But I didn't install this yet on this machine. So yeah, I actually forgot to add this piece on your machine, on your code base, but you could add this piece as well. So first of all, you install the package, make sure that it's there, which I have already done that actually by doing this installation here, which I have just done before that. And then open the library, set the working directory, which should be C. So now it's working directory C. And then if we get the library and some other library that we need to use, so I don't have our reshape, so I'll start that. Install grid extra. And then here is the dataset. Let's look at the dataset. Whoops. So this is exactly what we saw on the slides just now, meaning that those would be one of the data frame to carry the training, the other one is the cargo. So type, available, volume, profit. And here is trying to generate a LP model. So here is specific set. It's a linear program with 12 decision variables and 10 constraints. And then next thing would be how to set up those constraints. Starting from the first column and first row. And then trying to add all the constraints here. For each column, trying to add those constraints. Although we're not able to see the model, which is we are able to see it later actually. And also this set says sets the right hand side weight constraints, also the volume constraints. I actually hope that I can see that model. I remember that there is a way. And then here says the volume constraints and objective function, which is set.objective function. And then we write the LP out. Has not been optimized. Why is that? Just make sure that I didn't miss anything. I actually replicated this example like 3 hours ago. Somehow this has an issue here. So still cannot, but the thing was, this may not be the latest model that I had, but in general, let me find that, where, let me think. Seems to be the same as example. Yes, it's the same as the example. Yeah, that's exactly what I tried to do. I was trying to replicate that example for you guys so that you can, just to explain that example actually. Yeah, let me go there. Maybe I should go there and take a look. Yes, but in any case, we can. I'll try to solve this issue offline, but doesn't mention anything about optimization. It's actually not true because it's linear programming. So once we talk about linear programming, it would be optimization. So essentially saying that here, I tried to put some other things. Oh, it's here. So let's try to solve it. Why I cannot write it? It's what's weird. Suppose the model is already there. So here, so essentially here says the book. I mean the example in there said we can get once we get if it's 0, meaning if we solve the model and returns a 0, meaning we got a maximum, and then we can do some other things like get objective to get the value of the objective function, and then we can also do something like get variable. This is not explained in that example, but I hope that you can understand that get that constraints. Many other things that that's available. My point is many other things that's available for LP solve. We could use it in there. So if you look at the LP solve package, it has some other. It actually is it's a relatively new package that it's not a relatively new, but they have a new version recently. So it can solve many other issues, many other problems like LP.transport, which is some of the transportation problems. Make.lp. So Vincent, you are suggesting that make.lp didn't work out, or?
No, I was just saying that there doesn't seem to be any line that deals with optimization, so I don't know. I can't see anywhere in the code where it went wrong, right?
But here, for example, the last one here would be the optimization, right? Solve. I tried.
Yeah.
It's not there. It's supposed to be here. I just didn't.
Yeah, that's afterwards, right?
Yeah, that's the solve.
That's after you write the model.
Yeah, and then we can get the objective. But the thing is, this write didn't work somehow. But the output of the write is essentially just the results just like this, which is also in the slides, meaning that we can, if we have a mathematical function that we already wrote on a piece of paper, we could replicate in R, and then we can kind of say to cross-check whether it makes sense. That's the point here. And then I have another example actually, which is the shortest path. This one is also on the week 7 folder, and that's a link. I replicated that as well. I just hope that we could at least see some examples there. And then that's a data frame. Let's take a look at the data frame. So essentially meaning that we have some nodes, 234, 235, and the link between 234 and 235, the nodes, the distance is 21.6. And then they call it start ID, end ID, and the cost. The reason I have this example is because this particular package that's called iGraph can do many things that's beyond what we learned here. Hopefully in the future, in case that you need them, you can pull it out and understand more there. What iGraph does is it can do a lot of network analysis related, or the graph theory that we just went through, some very basic graph theory there. And then here, this is an example on the shortest path algorithm. So G2 is the graph. So because graph has so many things, again, something is wrong. Can be. Yeah, there you go. Because I didn't load the iGraph package just now. So now G2. The reason that we need to do this graph.dataFrame is because a data frame is different. It doesn't have this node, vertex, edge. It doesn't have this concept. That's why when we do this graph.data.frame, we can change a data frame to a graph, which is this G2. And then G2 become a graph. It has vertices and also edges, and the edge is called new cost. And the attribute for each node has some very interesting nodes there. So there are many other things that you can do for G2. For example, here I don't have it in the example, but it's like something like edges, if I remember correctly. No, but we can understand. For example, we could understand the G2 and then the iGraph, and then attributes for G2. I didn't say here. Okay. Print G2. We can see that graph. It's not here. Print G2 essentially just shows us what's the graph, and then compute the minimum distance from 324 to all other vertices. So 234 to 235 is 21.6, and 326 is 11. And then if we want to pick out the distance from 234 to 245, we could do this. And then we got the distance of 34.5. And at the end, there's some graph that we can take a look. So essentially, this is the original idea there. So to print out that graph, which is G2, if we PF2 is called. So the distance, as we can see here, 234 is connected to 235, 326, and 245. So 234 is connected to two of those, and there's another one which would be 234. Where is it? It's here. 245. That's the idea. So in this case, if we think about any of the graph that if we see on the internet on the many things such as we could use the width of the edge to represent the graph. That way we would see a different graph, and you would understand more on those graph theory. I mean graphs, how to do some network analysis type of problems there as well. That's everything that actually I want to cover today. Unless you have some other questions on these two topics, linear programming and graph theory, we can call it a day. So how exactly do you read that output? Which output? Rohan, yep. Which output? The train? Oh. So you are saying this model, right? Or you are saying about the results of
Yes, that right there. That right there. How exactly do we read the objective and the constraints right there?
how do you understand this? So let's go over, look at it. This here.
Are you referring to the results of the example code in which the solve and the get objective? Or?
Yeah, the fifth slide.
Are you referring to the model itself or referring to the results?
The results.
Oh, the results. Once you do the solve LP model, if you return a 0, meaning there is an objective. Meaning there is a optimal solution, and then you can get anything that you are interested in. For example, get the objective, and then you can also do something like I showed here. We can do get variables, the solution of the model, and get constraints. All this, and there are many other things that we can do with LP solve. That's why I refer you to the when we need it, right? For example, we may need to get shadow prices, margin value. We need to get the value of the two variables. But we actually don't go to that detail in this class, in this course. But in general, that's the direction that I'm pointing you to. In the future, in case you need to use some of these tools, you know where to do research, where to just get started.
So I guess I have a general question.
Yes.
You went over several of the graph models and problems and things like that, and it's been a little bit since I've dealt with graph problems. I was just wondering, is there a overarching algorithm or method to solve most of them, or is it on a case-by-case basis?
It's actually all linear programming. For example, if we look at go ahead.
For the graph problems that you went over?
Yes.
Okay.
For example, but this is actually I think it's chapter 8. It would explain.
Okay.
Let's say.
And so we'll be using R for some of the homework, or is it just?
It actually depends. It actually depends. If the specific says you need to use algebraic solutions, right? You have to enumerate all the possible intersection points and then do the calculation. Of course, you can use R to do the calculation that way. but that's not using LP-solve to solve that problem. That's option 1, meaning enumeration algebraically. The second approach would be simplex, meaning that you have to go through the
Professor, this is...
Go ahead.
Yeah, my question is there because in the linear programming homework, the same data was we have been asked to solve the same data using algebraic method, simplex method, and all other methods.
Right.
So my question is, if I have the solution, if I can solve it using R, why I need to do all these different methods?
Actually, essentially what R is implementing is simplex method. It's just
that's
like,
correct. My question is different. My question is, if I know how to solve that using R or whatever,
right,
then why I need to do my homework by hand, showing algebraic methods, showing simplex methods, showing all other methods? Because essentially we are not going to do that way. We are going to use some tool.
That's correct. But the thing is, just like if I tell you 25 times 5, we know it's 125, right? But remember that when we were in grade 2 or grade 3, we still have to find a way to solve 25 times 5. We cannot use Excel to give 125. You see what I'm heading towards? Because the simplex method is so fundamental that we still hope that you can do it by hand one time, right? So meaning that maybe next time when you see it, you don't want to do it by hand at all. That's the reason I didn't give you very complex examples that you need to multiple pivots. That pivot table thing, you don't need to do it like 10 times, 12 times to get a solution. It should be 3 or 4 iterations and then you are done. So I think it's better that you can do it. At least if you don't really want to do it by hand to simplex method, you can use R. I'm fine with that. You can use R to say, okay, boom, it's solved. But I still hope that at least you can read the example, understand what is simplex, so that next time when people talk about linear programming, you know simplex is the method that solves the problem. In other words, I'm sure this LP solve would mention, it's not here, but it would mention simplex in this solver. It's not.
Quick question.
Yeah, go ahead.
So it looked like the simplex method was pretty related to basically some linear algebra where you put the matrix in a DHR echelon form.
Yes, that's right.
Are there broader similarities, like with eigenvalues or different things that come into play in this type of thing? Or?
Simplex method, I don't quite think so. There's eigenvalues, all that. I don't think so. It's not here. No.
Okay, thank you.
Okay, no problem. That's this. And some logistics, just want to say that in terms of homework, what do you think? You think 4 is still too much, or you think it's something reasonable number? Because I don't really want you guys to have too much. I'm able to solve it while you with you. Okay,
I think it's more of a timing too.
Huh?
I think it's more of a timing too. See, the older class, if it has the same homework the same week, that's where the workload piles up.
Right.
If it's only this class, yeah, we won't have any problems. Like, for instance, this week we have the other class and this class.
Yeah.
And the other class has like about, what, 10 or 12, I think? Yeah. It's not weekly, but yeah. I don't know. I mean,
but
should we come with an alternate, like every week, every other week for each class, or I don't know what
that's actually more difficult for us to coordinate because I don't know how he planned on his course. But what I can do is, I think 2 probably not enough for you guys to understand the concept, but I can reduce the workload to 3.
I believe.
Go ahead.
Sharat, I believe we need to talk. We need to talk to that.
Need to talk to Paul.
Workload.
Go ahead. Go ahead.
No, need to talk to the other professor.
So for him, how many homeworks does he have?
We're working on the 3rd one right now.
But it's probably he only has like 7 for the whole semester.
Yeah, so he's reduced it.
Group assignments too.
Yeah, so he's reduced it to 1 individual week, and then the other week alternating to a group assignment.
I see.
So, yeah.
And then
it's not as bad now.
Not as bad. Okay. Okay. So let's do this on this class. The thing is, 3 homework I'm fine with. Even if you guys say, okay, let's just do 1 homework. That's okay. But the problem is, I still hope you guys can learn something from the course. If I have 4 homework, you guys can read the chapter and then work on those 4, right? Meaning that you would learn something. Otherwise, it's difficult for you to learn something. Yeah. So let's do this. Reduce to 3. I think it's probably a reasonable number. You can pick 3, meaning that I still hope one other thing that you need to do, that is, after I give you the solution, I hope I can be more responsive to. With that being said, I should have returned homework 5 and homework 6 by now, but I didn't do that yet. But by Sunday, I should be finishing homework 5 and 6, so that I hope you guys can actually spend a little bit time, 30 minutes also, to look at the solutions, which are from the fellow students, and some of them are really well thought of solutions. So can take a look so that you can understand what went wrong or what could be better for your homework in that regard. That's another way for you to learn. It's not like so in other words, I don't want you guys feel like pushed and didn't learn anything. Meanwhile, I hope you can learn something even though you felt pushed. But just don't worry too much about grades or anything. Just pay attention to what you can learn here.
I'm sorry, I think it just clicked now that are we only supposed to pick 4 of these the homework assignments we put out?
You didn't know?
Like for instance,
that's correct.
Is that correct?
Yes, but now we reduced to 3. Now you can pick 3. I'm going to send an announcement later.
I feel stupid now because.
No, actually, we just started like 2 weeks ago, I believe, right?
Okay.
Yeah,
that's correct.
Yeah, because I felt it was too much, and then I said, okay, let's pick 4 from now on, from week 4, I believe, or week 5. So from today, you only need to pick 3 of them. Of course, if you have more, I could offer extra credit, maybe 20% more for each homework. I'm going to think of this problem, this issue, and then send you an email. Maybe 30%. I'll think about it.
Harry, my take on those assignments was, like, see how the book picks those examples where it goes from one section to the next and it builds on the same example?
Right.
If you could do something like that, so we won't have to repeat the same work over and over again, and it can just keep building on the same problem.
Yeah, I could do some search on that book as well. I can try to do that. The thing is, when I set up all the whole structure of the course, when I pick up the examples in the summer, I don't have a clear understanding of everything as I stand now. Meaning that when second time when I read this book, I kind of feeling, oh, I could have done something better here. So I'm trying to kind of change the structure of the course and change the whole thing as well as we go along.
Okay.
Okay.
Yeah, for me the homework problems weren't too bad. I always, more so, not so much with the last couple of weeks, but it's always the reading that took the longest, I found.
That's true, because especially for this course, it's disconnected from chapter to chapter.
Yeah.
In some regard. And a good thing is from this point on, it's a little bit more connected, meaning that linear programming, graph, and nonlinear programming, and keep going, it's all kind of on the same concept. I actually want to show the vertex covers one of the problems, for example. I hope I can actually go over more detail of this math, but it's just we don't really have that time. This vertex cover problem is a integer programming problem. Minimize total cost, cover each edge of the graph. So the idea is that if I need to select a couple of nodes here, then every edge on this graph is covered, meaning there is a node that it is connected to, right? So in this case, for example, if I pick those three, all those edges are already covered, meaning there is a node, there is a red node that is connected to all these edges, right? For this one, the same thing. This is covered, this is covered, this is covered by this node, and then this edge and these three edges are covered by this and that, right? So using minimal edges to minimal nodes to cover all the incident edges. That's the idea for vertex cover, and it turns out to be a linear programming problem, as I just mentioned. And there's many other graph theory problems. They are all related to either linear programming or nonlinear programming. Majority of them are actually linear programming. Okay. So logistics-wise, I'm going to send you guys an email for the announcement of the homework, and probably let's reduce to 3. Every weekly assignment is actually quite demanding in my sense, in my understanding. But every week has new contents and new things to cover. That's why I have this weekly assignment. Especially we don't have anything for a final exam or midterm exam. That's why hopefully that you would learn things through homeworks. Another thing that I want to remind you is the discussion. Some of you guys actually don't submit the discussion, which I intended to have it to be there to give you 3 points actually. I wanted to summarize some of the discussion you have as well. Maybe next time I'll go over some of them. For example, I asked the question regarding whether some of the problems can be modeled as a queuing problem, and for those type of things, you guys can ask me as well. I can answer some of the questions as well. Do you have any other questions from any of you?
Do you have office hours? Dedicated office hours?
I can set up a dedicated office hours if you guys want to. I didn't have that there because I don't know everyone's schedule. How about
See, Mike on the other class, what he does is, he does, I think it's Tuesday or Wednesday, I don't remember.
Tuesday.
So when you have class, he
It's
has
on
office
Tuesday.
hours. I'm sorry, go ahead.
it's on Tuesday?
Yes.
Yeah, but
That's
in
right.
our case, if our homework is due on Sunday, I don't see the point of Tuesday office hours, right? Maybe Friday?
No, it's not just about homework. We can go over previous things or
Oh,
take the classes time.
okay, that's another possibility. Yeah, we can set up some office hour and then meaning that how can we get connected? You guys send emails or you guys we get connected through
Uses the
GoToMeeting?
GoToMeeting account.
Oh, okay. I can just use the GoToMeeting account and then I log in. In case you guys have questions, just log in and ask.
Yep.
Okay. Yeah, we can set something up. Okay. So if you don't really have any other questions, let's stop here today. And then, as I said, I'll try to send you the announcements and also try to check with Paul whether we can schedule another session next week as well, and possibly from now on every week as well.
Okay.
Okay.
Thank you.
Thank you, guys. Yeah, bye-bye.
Thank you.
Bye.
Good night.